Silicon. We are extending our lead. I think it's a given in the industry that Intel is the leader in process technology, and particularly in the deployment of that silicon technology in very, very high volumes. There's two feature sets I wanted to talk about just at a very high level. The first is strained silicon, which we first implemented in 2003 on 90 nanometers. We're on our fourth generation of that. When we introduced strained silicon in 03, it gave us the ability to pop transistor performance by 25%. And so every increment has basically been able to maintain at least that capability generation to generation. But as we went into smaller and smaller lithographies, obviously the power issues became paramount to us in terms of leakage. And we dealt with leakage, I think, in a very clever fashion by inventing high-K metal gate. Right? And we are now on our second generation high-K metal gate. We put it in at 45 nanometers. We're shipping 32 nanometers now in high volume. The first generation of high-K metal gate gave us a 10x reduction in leakage in terms of lower leakage power. And the second generation, 32 nanometers, gave us another 10x. So that gave us the ability to start taking the power envelopes down at the same performance, or having very good performance at much, much lower power levels, as you'll see from Dottie on some of our handheld chips, or in the server arena, be able to maintain the power envelope and take performance up substantially. All this is being done through the magic of Intel silicon technology. We are on strained silicon, depending on who you look at, 1 to 3 years ahead of the competition. And on high-K metal gate, 3 plus years into this, we're still the only company in the industry shipping this technology. And we ain't finished yet as we move on to 22 nanometers and beyond. And Bill will give you an update on that a little bit later on. Why is transistor performance important? Because performance matters and power matters. And here I've picked an older technology from Intel, 45 nanometer, and I've compared it against the current shipping technology from TSMC and IBM. They're high-end technology. So sort of our 2-plus-year-old technology against theirs. But I thought it was an apples and apples comparison. And you can see on NMOS and PMOS transistors, our ability to drive current, think of the drive current as a measure of performance. You want to be higher on both these scales, right? And at a given power level. And so what we've been able to do is generate about 25% higher performance, or conversely, if you're building a low-power device, 25% lower power than the comparable technologies from TSMC and IBM and Samsung and others in that same league. And I could have made this more extreme by showing our shipping 32 nanometer against theirs, and you'd see another 20-25% performance on top of that. So this continues to give us the ability to build better products. This is particularly, obviously it's important in our mainstream microprocessor business, where you want to be able to optimize that power performance against classic benchmarks. But it's going to be increasingly important for us as we move into the area of handheld and consumer electronics and embedded systems, areas where the Intel architecture is not the incumbent. And we need to come against other architectures that are shipping in high volume there and be able to do so while offering the advantages of our architecture, the opportunity to have very low costs, the opportunity to meet or beat the power envelopes that are required to be in those business, and then the value proposition of Intel, which is higher performance and software compatibility. And we think that we've got the technology now to deliver on all the vectors necessary to be competitive here. And you'll see some examples in terms of demos from the guys later on today. Another thing we've worked on is what I call square wave transitions, moving much faster with a new technology into the marketplace. I'll show you some examples of this. In the old days, we would show you these X curves of technology A crossing over technology B and so forth. It's less and less relevant because we're moving to an environment where we are moving towards shipping new technology out of the gate almost on an all-in kind of basis. 90 nanometer, which is a circa 2003 technology. When we launched that technology, the state-of-the-art product was a Pentium 4, single-core CPU, 170 million transistors. And it took us 50 weeks or so to reach sort of the high volume point of that product line. Fast forward to 32 nanometers, 4 generations later. We did that same ramp in terms of unit production in roughly half the time, right? On a much more complex set of products. Here, the products that we built were anywhere from 1 to 6 cores, CPU cores on a die. We integrated the memory controller, we integrated graphics, we have I/O integrated now, and we integrated the capability to do Intel wireless display. So much more complicated devices. If you want to measure the transistors, sort of almost an order of magnitude more, 1.1 billion transistors. And we're doing it twice as fast to the same volume. So what? That allows us to be able to have these introductions where we take and refresh an entire product line like we did in servers, like we did in the laptops in the January timeframe, and go very, very fast to market and coordinate our marketing campaigns with our production ramp, with our customers' need to switch over. And therefore, it minimizes their need to manage the inventory and have some of the overhang that we used to have, which was, quite frankly, problematic in the industry for decades. How do you sell the old stuff when the new stuff is ramping? Right? The faster you can ramp the new stuff, the less of a problem that is. And we've gotten very good at this by moving towards what I call the square wave transition capability. The next point I wanted to talk about is our architecture. And I think there's those out there that say, well, Intel ships a lot of volume, but in the grand scheme of things like ARM, so what? Well, this is so what. This is the cumulative processor cores shipped by Intel Corporation through this quarter. So it's a projection through Q1 of 2010. We'll be at 3.3 billion cores, microprocessor cores, and you can see the slope of the curve. It really has gone up quite dramatically in the last couple of years. By the way, by the end of this year, that number will be closer to 4 billion cores. So what's relevant about that? This just says that the architecture, which is the most popular on Earth, the one that has 14 million developers writing to it today, which is IA, is getting more popular every day. We're building up our installed base. We're building up the software base around our products. We are still the only high-volume architecture that offers forward and backward compatibility, generation to generation, to preserve that software investment. And we think that's the key for us to be able to enter these new markets, because we bring software with us, we bring 14 million developers with us, we bring all the tool sets with us, we bring the ability to run the web with us, core after core, billion after billion. And this is only going to get bigger. If you extrapolate these numbers out over the next couple of years, you're dealing with tens of billions of IA cores out there as an installed base.